welcome.
Okay, thank you very much. It's very nice to be in Types here. So this is my favorite conference, actually already for a long time. I haven't been to all Types meetings, but I think it was at the first one, which was actually called Logical Frameworks, and it was in 1990 in Antibes, which was also a very good place actually. So, and I think there's one person here in the room that was definitely there. Maybe there are more. I don't know whether there's a unique existence, but there's one person definitely was there, and he's waving his hand. Was Hugo there in Antibes as well? Okay, the two. Okay, so I said at least one, but okay, Hugo. Yeah. So, okay, so then you know who the old guys in the room are. So that's. So it was very nice because Jean-Yves Girard was there and Pierre Martelov was there, and there were hefty discussions in the evening about predicativity versus impredicativity. So that was very nice. Yeah. Okay, so those were the old times. So you may know that the Types meeting has gone up and down for various things. So it's very nice. It has been almost dead, almost at a certain point. But and I didn't always go, but very nice to see 150 people here and young people, and especially keep the thing going. So now back to the talk. It's also old-time stuff. This is a problem that I kind of was already there. So in the beginning of the 90s, and I'll talk a little bit about the history, but I won't tell too much about the history. And there's also a disclaimer. So it's about type theory. It's very much intentional. So that's one thing, and it's very much about syntax. So a lot of this is about semantics. This is just about syntax, and actually it's a little bit about untyped lambda calculus. So let me just see whether the next slide is coming up. Yeah, so fixed point combinator. So why is a fixed point combinator? So why actually do we want a fixed point combinator? So the fixed point combinator gives you a fixed point. So if you need a fixed point of m and you have a fixed point combinator, then you just apply f to m, you have a fixed point. So that's just everything you can say about a fixed point combinator. So why is this useful? Well, it's very useful. You can solve recursive equations. So if you think, is there an m that satisfies this equation? And if you squint very clearly, then you think, oh, this is a function that actually defines the factorial. Suppose I want to define the factorial, I need an m to solve this. And the nice thing about untyped lambda calculus, if you have a recursive equation, there's always a solution. What is the solution? Well, here's the solution. It's just your favorite fixed point combinator applied to this higher order variant, this thing. So that's extremely cool. Okay, so that's why fixed point combinators are interesting. And of course, you have your favorite fixed point combinator. So here's some favorite ones. This is Curry's Y fixed point combinator. This is Turing's theta fixed point combinator. And probably if you've never seen a fixed point combinator, you can just randomly choose. Other people typically have one of these as favorites or have their own other ones. I have another one, which is my favorite, which is this one actually. So this is L. That's not a very well-known fixed point combinator. You may not even believe it's a fixed point combinator, but here I've written it out. If MF is this funny term here in the middle, and omega is just this thing in the back, then you see that LF is omega, MF omega, MF, MF omega, and you get that one. So, okay, so it's a fixed point combinator. And I'll tell you later why this is my favorite fixed point combinator. Or maybe I'll tell you now. L is typable in lambda u, and y and theta and big omega are not typable in lambda u. So that's actually the story here. Right, okay. Now what is lambda u? So some of you know lambda u, and some of you don't. So I'll briefly try to explain also to the people who don't know yet what that is. Okay, so this is lambda u. It's actually higher order predicate logic over polymorphic domains, which means that you have two impredicative sorts on top of each other. And we all know that that's inconsistent because that's not in the rock system, basically. So it's all the combinations that are not in the rock system. So what is that? So in rock, you can think about prop and type 1 and type 1 and type 2, but I will write star and box and triangle. Okay. And the thing is that star is basically prop, and that's impredicative. That's our formulas. And box is where the data types live, and that's also impredicative, but that's on top of the one about formulas. So you can write this kind of knot, the poly knot, If we think of polyknot, it's now on the kind level. Okay, so there's various ways. I will call the things in here types and the things in there kinds, because that's how we used to do that at the time. Okay, so lambda u also allows quantification over this whole universe. So you can write this. And lambda u minus is if you don't do that. So lambda u and lambda u minus are slight variations. And they're both inconsistent, by the way. Okay, so what's the history here? So Girard called this system U and showed it's inconsistent in his PhD thesis. If you like reading French and old documents, you can still read it. And it's a very short proof, actually. And you really think, that went fast. So after that, not soon after that, Pierre Martin-Löf came with his proposal to have a system with type colon type. And Girard immediately kind of, by return mail, told him, that's not going to work, because if lambda u is inconsistent, then this one is also inconsistent for trivial reasons. So what do we mean with that? Well, we mean that there's a term of type bottom, and this is bottom, which means that there's terms of all types. And you can easily see that a term of type bottom does not have a normal form. That's not, it's purely some syntactic inspection that cannot be a normal form. All right, now there were some questions here. So there's been going on after this. Girard asked the question whether lambda u minus is inconsistent. If you kick out this polymorphic, this higher order quantification. And Coquin in 1994 showed yes, that's also inconsistent. And in 1994, Tony Herkens gave a very short proof of inconsistency. And why is that nice? Well, you can actually write down the term on a whiteboard and you can look at it. And you can play with it and cuddle it and that stuff. And so you can even make a picture out of this. Okay, it's very nice. Okay, but it's actually, you can operate with that, so that's very cool. Now, what is computationally going on with lambda u? Well, when we go back to Howe in 1987, he had studied Coquin's version of, so the proof by Girard is pretty hard to digest. So Coquin gave an explanation of that in 1986 at LIX. And Howe took that and transformed the term bottom into a term of type alpha with an f of type alpha, and showed that this mf you get here actually gives rise to a looping combinator. So what's a looping combinator? That's actually a family of things such that lnf is not exactly f of lnf, but ln plus 1f. So you can keep on going there. And if you know the proof how to do partial recursive functions using a fixed point combinator, then you see that this is enough, because the only thing you need is to get as many f's in a row as you want, basically. So that's the looping combinator does that for you. Okay, so that's a Howe's clear, a good contribution. And also that has been going further a bit. Well, in various, I mentioned Coquin and Herbelin, so they showed that this can be carried out very generally by a translation definition. And I myself and Randy Pollack in 1995, we analyzed Herkens' proof, and you see that indeed you get a looping combinator, Ln. So it means, so maybe you can, so logically you can do everything in lambda u, and computationally you can do everything in lambda u. So can you do everything in lambda u or lambda u minus? Everything I say about lambda u and lambda u minus, it's all the same. You may wonder, are all untyped lambda terms typable in lambda u? So the answer is no. Is there a fixed point combinator in lambda u? Don't know. So that's one of the open questions. Right, let me say something about lambda u. So if you really like concise definitions, this is lambda u. It's, oh sorry, where is it? We're going back a bit. This is lambda u is a pure type system. And if you're more into ROC, then you can see there's prop in type 1 and type 2. And the main thing is that everything is safe and sound here, except for this red bit here. So everything you have here, you have in the ROC system. You can quantify from prop to prop and eliminate from type 1 to prop and from type 2 to prop. The only thing you cannot do is this. There's no pi type on this form, and that's actually the odd one out. I also singled out the green one because if you kick the green one out, you get lambda u minus. Okay. Now, why is lambda u such a nice system? Well, you can really give a kind of stratified presentation of it. So if you kind of separate the variables a bit, and you can really separate the things much better than in lambda star in terms of kinds and constructors and proof terms, and the types are a subset of the constructors. And you can do that in this way. So here I use specific names for specific classes, like kind variables are k, constructor variables are alpha, proof term variables are x, so I really use the special symbols for that. And if you want to see how that all kind of hierarchically lives, it's this. Okay, what does this mean? It means that we have proof terms which are of types. So here P is of type of sigma, which lives in star. And you have constructors which live in a kind, which lives in box. So there's always three levels here, but they're kind of separated from each other. So on the proof term level, you can do all kinds of applications and abstractions. On the constructor level, you can also do all kinds of abstractions and applications. And on top of that, you can form these types. So you can arrow types between types. And this is the higher order quantification for types. And on the kind level, you can make arrows between kinds and do the polymorphic definition of a kind. And this is the thing that makes the whole thing inconsistent. Okay. Now this nice stratification, why am I giving this to you? Well, there's an important point here that if we forget about the proof terms, everything here is just normalizing. So the non-normalization is really there, even though the funny thing is there. So that's a bit awkward or a bit strange at a certain point. But the good thing is that type checking is decidable. So lambda u is inconsistent, but type checking is just decidable. And that's very helpful if you want to analyze a little bit what these terms all do. Okay, so that's just a lemma. We have to do some proof, but it's not really difficult to show this. The type level thing is basically system F omega maybe, but something like that. So that's very well known to be normalizing. Okay, if we know all this, we can also define what we usually call an erasure operator. So we erase all type information. And that's all type information, so that's everything that has to do with this level. So I'm only having the typed, untyped terms. So I reduce type information, but if I abstract over higher order things, I just remove everything. So the only thing is there. And what do I mean when I say that M is typable in lambda u? I'm saying that there's an untyped term, M is an untyped term, and there is a Q that lives, there's a proof term of type sigma, and the erasure of Q is M. So that's actually really the problem which I'm looking at. Is Y as a fixed point combinator typable in lambda u? And the answer is no. Okay, so how do we do this? So this is the main result. So the main result is that omega and Y and theta are not typable in lambda u. And that's a more general theorem in a sense. And the general theorem is that you cannot do double self-application. So if you have a term, maybe we can look at it here. So if you have a term where you have an XX and a term with a YY, you cannot apply those to each other. So this is what omega really looks like. And Y also has this shape, and theta also has this shape. They have a shape of double self-application. And that's not possible in lambda u. That's a story. Okay, so now we get a little bit more technical. I don't know how much time I have, but the chair will actually tell me to stop at a certain point, a few minutes. Okay, let me go. So what do? We look at parse trees. So parse trees of types. And now it's very cool. The types are all strongly normalizing. So I just look at normal forms. So this is a parse tree. It either looks like this or like that. And I'm really looking at this parse tree and I'm going down the left branch. I'm very interested in the length of this left branch. and the alpha that I in the end find, because that's what I call the head variable. So if I go left down, at a certain point I hit up in this form, and that's my head variable. Okay, so there's a left terminal path, that's interesting, and I said this alpha is the head variable. And you can talk about types being contained in each other. So basically, if it's just a type, you can instantiate some of the V's and you can do some abstractions. That's what I call containment. And the nice thing to know, if the sigma is contained in tau, then the length of this left terminal path is less than or equal to the left terminal. That one. Okay. Right. Now, sometimes this guy is really less than that one. Well, that can only happen if this head variable is bound at the root of this parse tree. Otherwise, that cannot happen. So that's an important lemma, some kind of syntactical analysis, not really difficult, but you have to look at that. And then we have this important proposition. If T contains a self-application, then this head variable is bound at the root of this parse tree. And here's the proof, and I'm going to skip it. Okay, as a consequence of the lemma is actually the main theorem that we do not have a typable term of this form. And here is actually also the proof is on the slide, and actually what I put on the slide is basically the whole argument. Let me go through it a bit. So what does this look like? If you have a typed form, it looks like this. And Q has that type and P has that type. And the head variable of sigma is bound at the root of sigma, and the head variable of rho is bound at the root of rho. But sigma is beta equal to this. So that cannot be the case. So this is a contradiction, and therefore it cannot be well typed. So that's actually the whole argument. There is some gory details that I'm skipping over now, but that's the argument. Okay, so that's the conclusion. I just in time came to the conclusion. Okay, so the following well-known terms are not typable in lambda u. And this thing, my favorite fixed point combinator, is typable in lambda u. Actually, that's the one you get from the Herken's paradox. And you see it does not have double self-application. You see a self-application here, and this thing looks a little bit suspicious like self-application, but it's not. So it's kind of just not. If you look at the full typable term, L, because it's really full typable term, is really a looping combinator. And the looping is really due to all kinds of information in type labels exploding, basically. So that the type labels get bigger and bigger and bigger. So computationally, it's really this thing. Okay, there's lots of other things you could work on here. There's still a question whether there is a fixed point combinator, and you may wonder whether these guys are typable in lambda star. My personal conjecture, but I didn't put it on the slide, is that it's no, but I have no idea how to prove it. Thank you.